Hi, I'm Lev from Fetch Robotics, and this is Zoo, also from Fetch Robotics, who couldn't be here today, but was a big part of this project. So I'm going to start off with a quote I love from Stack Overflow, which is, developers these days don't know how to deploy code, so they just ship their development environment instead. So let's talk about shipping our development environment. So there were a couple of goals when we started this new release pipeline, which was to keep update sizes as small as possible. Warehouses are Wi-Fi starved, so we don't want to put too much pressure on their bandwidth. We wanted to minimize the time and effort it takes to make a release. And we wanted to make upgrades and downgrades hermetic so that we were comfortable upgrading or downgrading a robot in the field. For development, we wanted to make it easy for multiple developers to have multiple versions on one robot. Robots become a scarce resource when you're developing, and you don't want to fight it out. We wanted to make it so developers can build a release locally to test things out, make our developer testing in production environments the same so we can catch bugs early, make setting up a robot easy so that our web and cloud guys can try out things without necessarily having to know the robot codebase, and we want to minimize time spent compiling because it's boring. So a little preamble on Docker. It's a form of containerization. It encapsulates your system dependencies, environments, executables, even something like an operating system. It's not a VM, but it provides a similar kind of isolation while using the underlying kernel, so you don't have much virtualization overhead, and it should run pretty much the same speed as native. It's built using Docker files, so they're kind of files that describe how you're going to build an image. And Docker Compose is a way of running one or multiple containers. It relies on this concept of image layers that can be cached, reused, and transferred, which is quite important, so I'm going to dive a bit deeper into that. So this is what a very simple Docker file might look like. You have a series of commands that you run that maybe mutate some data or echo things, stuff like that. And you build it, and you get an image. So if you run it again, all of this is cached. And when something is cached, it means that you already have an image layer. So every command you run creates an image layer, and the final image is just a collection of these. If it's cached, you don't have to rebuild it. And if you pull a new version, you don't actually have to download anything because you have it locally. So if I change a command, let's say I echo a different thing, then the layers below it get broken, and they would have to be rebuilt and re-downloaded if you're trying to pull a newer version. If I do it somewhere lower down, the lower down levels get broken, but not the ones above it. So there's also this concept of a context, which is the folder that your Docker file is in has a bunch of files that are available to the Docker as you're building the image. So in this case, we have some data file that we're copying. And copy is a little bit special in that it will first pull in the data, then check if it's changed before breaking the cache, as opposed to a run command, which will only break the cache if the command itself changes. So in this case, if we run it again, everything is cached, no problem. But if we change the data, now the cache is broken, and it has to rebuild and be re-downloaded. So multi-stage builds kind of extend this idea from outside of the context to a Docker stage before your main Docker stage. And it can kind of replace a bunch of build tooling that was needed before. So in this example, we're doing the same thing, except our data file is generated from a previous stage. If we run it again, everything is cached. If we change a command, because the stages are cached independently, as long as the data is the same, the next stage will not be broken, and so you won't have to rebuild or re-download. But if we change the data that's being copied over, the cache is broken, and we rebuild and re-download. So this is sort of the structure we've come up with, which means absolutely nothing right now, but let's step through the stages. So we start off with a frozen stage, and this represents your slowest changing dependencies. So this could be something like your operating system, or if you have a frozen version of ROS, stuff like that. You want to cram as much as you can in here because since this doesn't change often, it doesn't need to be re-downloaded, which means your update sizes stay small. And this is a very simple one, what it might look like. So then there's this idea of secrets used during build time. They can be SSH keys, they can be passwords. A regular Docker file has the disadvantage that any argument you pass in is sort of stored in the final image because it's a collection of all the images. We generally don't want that with SSH keys because then you're leaking secrets. So we can use multi-stage Dockers to sort of get around that. We pass the argument to only the stage that, let's say, downloads a requirements file. The next stage copies only the requirements file, and in its final layer doesn't know anything about the secret, so you don't risk losing your password. So this plays well with the cache breaker stage. This is because run commands are cached if they don't change. There are some commands that you'd want to run every time. Let's say git pull, the contents of the pull might change even though the command itself doesn't. So again, we make a stage before the main stage, and we pass in a randomizer argument. And this randomizer argument could be a hash of the date value, for example. Because the argument changes every time, the cache breaks every time, and we run the wget every time. But as long as the requirements file itself doesn't change, the next stage, when it copies it, will maintain its cache and not have to be rebuilt. So this is pretty important for the first stage in the pipeline after the frozen stage, which is the base stage. So the base stage will copy over from your source code only your requirements files or the equivalent and install all your production requirements. The idea here is that it only really changes for major releases. So for minor updates, it doesn't change and the updates remain small. So at the end of this stage, you should sort of have all of your production requirements. So if you copied in your executables, you would be able to run. From this stage, we go to the dev base stage. Here you do something similar, except you copy over your developer dependencies as well and your source code. So at the end of this stage, you should sort of be ready to hit catkin make and be ready to go. But we only do that until the next stage, which is the build stage. And the reason we do something like catkin make in the build stage is because compiling code touches a lot of files, changes a lot of files. And as I said before, every time you change a file, it makes a copy of it in the next layer down. And that'll introduce a lot of bloat you don't want to go into your production image. So we pass our build stage and get to our dev stage. And this sort of inherits from the dev base stage, and that has all your production and developer dependencies, but also has your built binaries from the build stage. So at this point, you could give this to a completely new developer instead of them having to spend a day or 2 days trying to set up their own development environment, and they're ready to change code and compile right away. Similarly, we have the production stage, which would pull only something like, let's say, an install folder from your Catkin workspace and leave out all the other sort of developer data. And you're ready to ship this to a robot and have it run right away. There's some extra optional stages. You can include, such as a continuous integration stage, which would inherit from your dev stage. So what you could do here is you could pull in, let's say, a pull request and build and run the test right inside the Docker, and you know that the environment is the same as production and development. You could also have a live test stage where you take a development Docker and put it on a robot in a test warehouse. If anything goes wrong, you have all your source code there for you to play around with and debug. So there's been several developer benefits from changing to this pipeline. We can now have different versions with mutually exclusive dependencies running on the same robot. So let's say somebody's working on Ubuntu 14.04, but somebody else wants to upgrade to Ubuntu 18.04 for the new stack. Well, they can both be on the same robot, even at the same time, although that's probably inadvisable, and not be on each other's toes. One person runs their Docker container, stops it, the other person can run it right away. There's no switching dependencies. Similarly, if there's another developer that always deletes files you need or changes the environment, they can't hurt you anymore because you're in your own separate sandbox container. So you can just stop their container and start yours. There's release benefits, and that now our entire build pipeline is roughly 300 lines of Docker file, replacing a bunch of scripts that were sometimes semi-manual. Releases are now nightly and on-demand and take under 2 hours instead of a day, and anyone can trigger one. Before, Zoo, who was our DevOps guy, would have to trigger a build. So if we need an urgent patch, we would need to call him at home and offer him free dinner. Now it's a lot cheaper. Building a release candidate just takes GitHub, SSH keys, and Docker, literally nothing else. So you can be on a brand new computer and be building a release of our entire stack in a few minutes. There's also deployment benefits, and since everything is in a container that comes from a sort of master image, if something goes wrong in the field, we can change environments or files or code and not worry that if we break something, it's unrecoverable, because if we break something, we can just get rid of that container and instance a new one. And upgrades and downgrades are one-shot now, which means that before an apt install might fail in the middle, and you have a sort of in-between robot that's hard to debug. Now we don't have to worry about that. It either works or it doesn't, and all the robots have the same exact environment and code running. There are some considerations that come along with it. We've talked a lot about layer and image size and how to make updates small. So now that's a very first-class concern you have to worry about. Changing a layer high up in the chain, let's say the frozen stage, can cause large updates, up to 2 gigabytes in our case. But it comes with a workaround that now it's very easy to download an update in the background without worrying about halting operation in the middle. Another problem is that with unserved binaries and caches such as Ccache or Bazel, dev images can get up to like 20 gigabytes in our case. So that's a lot of bandwidth you're using internally. And that requires new infrastructures such as local and cloud registries. That's about it.
Thank you for interesting presentation. I have a question regarding reverting changes. That's my first question. So you have a Docker container with the newest changes, and somehow it appears that they are not working correctly. Mm-hmm. How can you revert? And the second question, so this development image, so it only has compiled source code and source code. Do you have any development environment there? And if yes, how do you deal with different graphical cards issues?
So for the first question, so when you create a container, you're doing it from a master image. So in that container is where you make your changes, and it's like having a sort of VM, but Docker people hate calling it a VM. So if you do something wrong and break it, you can just delete that container and reinstance from the Docker image as opposed to the Docker container. And that way you revert all of your changes. For the second question, there's a bunch of ways you can sort of have a development environment. There's a lot of ways to do it. You can mount all your folders for the Docker and do it from the outside. I like to do something dirty, and I go into proc ID and use a pseudo editor, but I do not recommend that. And then other ways are doing like a SSH into it and mounting the file system through SSHFS.
Did you do any analysis, or do you have any experience in performance degradation using Docker on a robot, like additional jitter or additional latency or something like that?
So we've been running it in production for a while now, and we haven't noticed any increased performance hit. Ideally, it should be the same as native.
Well, can you hear me?
Yeah.
I'm trying to use also Docker myself, and I love all the benefits. But when you try to do hardware in the loop simulation, so where you need to simulate the environment but still run on the robot, I don't know if you have that particular need, but it's not super straightforward to get all the networking up and running, and also the displays issue. So I was wondering if you have some documentation on that you had to generate internally, or some tips.
Unfortunately, I don't have any documentation, but we do have hardware on the robot, and we do have displays on our robot as well. So we've had to deal with networking interfaces and display interfaces. There are solutions. Some of them are like using the network in host mode, or doing dirty things to the X authority, but there are ways around it.
Right. Okay. Thanks.
If you had to start from scratch again, building this system, would you use Docker again, or a different container system, or something else? What technology would you choose?
That's a good question. I would probably choose Docker again, because it's also what we use on our cloud and website. So it's kind of nice having it be consistent, and people can sort of work on both because it's common knowledge.
Hi, this is super cool. We considered Docker, and there were 2 issues with it that made us not choose Docker, and so I'm curious how you've dealt with them. One was kind of the outer system concerns of like UDEV rules and systemd units and like the kernel itself. That if we built a fancy Docker infrastructure that let us upgrade everything except those things, we'd still have to build a way to upgrade those things. And if we had to do that anyway, it might as well upgrade everything. So that was one issue. And then the other one was like persistent storage issues, like bags, logs, maps, all that kind of stuff. Like, do you put those in the container so when you downgrade, you get the old version of them? Or are they in a shared storage pool that you have to kind of manage outside the container?
So I'll start off with the second question. For things like bags or other things specific to the robot, such as, let's say, calibrated URDFs or configurations, those are in mounted volumes, so they're not in the container itself. They're sort of on the regular file system. For your first question, yeah, we've had to consider the kernel thing as well. We've not gotten all the way to where we're updating the kernel, but we do update UDEV rules, and unfortunately, Zoo is the one that knows more about that, and he's not here. But if you talk to me, I can give you his email.